Welcome to a unique kind of workshop. Today, we're not building a machine or busting a myth in the traditional sense. Instead, we are going on a journey through the very building blocks of our universe. We have a simple tool, a very, very sharp knife. Our mission is to slice through every stable element on the periodic table. We're going to treat each one with the same process, under the same conditions, in super slow motion. Now, this isn't just about destruction, it's about observation. It's about understanding the fundamental properties of matter by seeing how it reacts to a simple, controlled force. This is exploration at its most basic and most revealing level. The setup is straightforward. Each element is secured in a vise. A high-speed camera is trained on it, ready to capture every detail at thousands of frames per second. Our knife is made of a theoretical, impossibly hard material so it won't dull or break. It will move at a steady, slow pace, allowing us to see everything. What does the surface look like before the cut? How does the blade enter the material? Does it deform, crack, or slice cleanly? What does the newly exposed surface reveal? These are the questions we're here to answer, one element at a time. This methodical approach is key to seeing the subtle differences that make each element unique. Our experiment begins with the lightest elements and works its way up. We're going to see an incredible diversity of behaviors. Some elements will be soft like clay, others will be brittle, shattering like glass. Some will be shiny while others will be dull and dark. We might even see some react with the air the moment they are cut, changing color right before our eyes. The goal here is to build a visual library, a mental catalog of textures, colors, and reactions. This consistency in our method is what will allow us to compare a light, reactive metal like sodium to a dense, noble metal like gold. Let's be clear about the parameters. We're doing this in a controlled environment, an inert argon atmosphere, to prevent unwanted chemical reactions with oxygen or moisture. This ensures that what we see is the true nature of the element itself, not the result of it burning or tarnishing. Safety is paramount, even in this thought experiment. So, with our lab coats on and our safety glasses firmly in place, we are ready to make the first cut. We are peeling back the layers of the universe one slice at a time to see what secrets lie just beneath the surface. It's time to begin our slow-motion journey through the periodic table. First up is lithium, element number 3. It sits in the vise, a silvery white block with a faint hint of tarnish. It looks surprisingly light, almost like a piece of dense metallic wood. The knife begins its descent. As the blade makes contact, there's no resistance. It sinks in effortlessly, as if we were cutting through a block of cold, firm butter. The slice is perfectly clean, leaving behind a smooth, almost wet-looking surface. This newly exposed face is incredibly bright and shiny, a brilliant mirror that reflects the lab lights. But almost instantly, you can see it start to dull as it reacts even with the trace impurities in our argon atmosphere. Next, we have sodium. It looks similar to lithium but even softer. It has a waxy, silvery appearance. As the blade approaches, you can almost anticipate the ease of the cut. The knife glides through the block with zero effort. It's even softer than lithium, more like slicing through a refrigerated block of cheese. The cut surface is stunningly bright, a liquid-like silver sheen that is almost dazzling. The texture left by the blade is flawless, with no tearing or jagged edges. Like its cousin lithium, the shine begins to fade quickly, a visible reminder of its extreme reactivity and its eagerness to bond with anything it can find. Potassium is next in line, and it's even more dramatic. This metal is so soft that the pressure from the vise has slightly deformed it. It's silvery, but the moment it was placed in the chamber, a faint purplish-gray oxide layer began to form. The knife touches down, and it feels like there's nothing there. It slices through the potassium block as if it were a block of cream cheese at room temperature. The blade leaves behind a surface so shiny it looks like a pool of mercury. The reaction is immediate. The brilliant silver flashes for only a millisecond before a violet-gray haze clouds over it, the element tarnishing right before our very eyes in slow motion. Finally, we have rubidium. This one is special. It's a soft, silvery white metal, but it's so reactive that keeping it pure even for a moment is a challenge. The knife descends, and the cutting process is less of a slice and more of a smear. The metal is incredibly soft, like partially melted wax. As the blade passes through, the material deforms and flows around it. The freshly cut surface is a brilliant, almost blinding silver, but it vanishes in a heartbeat. It oxidizes so fast that you can see a dark layer chasing the blade's edge across the block. It's a beautiful, fleeting display of pure elemental energy. Now we move to a different neighborhood of the periodic table. Let's look at aluminum. This element is familiar to all of us. In the vise, it's a light, silvery gray block, instantly recognizable. As the knife begins to cut, we feel a distinct increase in resistance compared to the alkali metals. The blade doesn't just sink in, it has to work. You can see the metal compress slightly just ahead of the cutting edge. The slice is clean, but it produces very fine, almost microscopic shavings. The new surface is bright and reflective, but it has a more muted, satin-like finish than the brilliant alkali metals. It holds its shine, protected by a transparent passive oxide layer. Next up is lead. This is a classic dense metal. The block in the vise is a dull, heavy gray. It has a certain visual weight to it. The knife makes contact, and the experience is completely different. Lead is incredibly soft for such a heavy element. The blade sinks in with very little effort, but it's not a clean slice. The metal is so malleable that it deforms and smears, leaving a slightly rough, torn texture behind. The freshly cut surface is a surprising bluish-white, quite bright and shiny. However, it quickly dulls to the familiar gray as a new oxide layer forms, showing us its true, unweathered face for just a moment. We now turn to tin. In its common form, beta tin, it sits in the vise as a silvery, malleable block. It looks a bit like aluminum but feels heavier. When the knife starts to cut, something amazing happens. As the blade shears through the crystalline structure, you can almost hear a faint, high-pitched sound, the famous tin cry. In our slow-motion view, we can see the crystal boundaries deforming and breaking. The cut itself is relatively clean, but not as smooth as aluminum. The new surface is brilliantly shiny, like a fresh piece of tin foil, and it resists tarnishing much better than lead, holding its luster for us to observe. Our final element in this section is bismuth. This one is a showstopper. The block itself has a slightly pinkish silver hue and is surprisingly brittle. The knife touches down, and instead of slicing or smearing, the bismuth fractures. The blade acts more like a wedge, causing tiny iridescent crystals to cleave and break away. We don't get a smooth-cut surface, instead we get a fascinating terraced landscape of geometric shapes. The newly exposed faces are incredibly shiny and reflect a rainbow of colors, an effect of a thin oxide layer that forms instantly. It's less of a cut and more of a beautiful crystalline shattering event. Our exploration now takes us to the fascinating staircase of the periodic table, the metalloids. We start with silicon, the heart of the digital age. In its pure crystalline form, it is a dark gray material with a distinct metallic luster. It looks like a piece of polished metal, but we know it's different. As the ultra-hard knife makes contact, there is no cutting, there is no smearing. Instead, with a sharp crack, a fracture line races ahead of the blade. The silicon shatters like glass, breaking along crystal planes into sharp, angular pieces. The newly exposed surfaces are smooth and highly reflective, but their brittleness is undeniable. It has the look of a metal, but the soul of a non-metal. Next, we examine germanium. It sits in the vise looking very similar to silicon, a hard grayish-white and lustrous solid. It has that same metallic yet not quite metal appearance. The knife descends and the result is almost identical to that of silicon, but with a subtle difference. It is still incredibly brittle, and the blade's pressure causes it to fracture rather than slice. However, the fractures seem slightly less explosive. It cleaves cleanly, creating flat, mirror-like surfaces. The pieces that break off are sharp and well-defined. It's another perfect example of a material that looks tough and metallic, but behaves like a brittle ceramic when force is applied. Now for something different, arsenic. In its gray metallic form, it's a brittle steel gray solid. It has a semi-metallic sheen, but it feels less dense than a true metal. When the knife attempts to slice it, the result is predictable yet fascinating. The arsenic block doesn't deform at all, it simply shatters. The blade's edge initiates a series of cracks that propagate through the material, breaking it into smaller granular pieces. It's like trying to cut a lump of coal. The freshly broken surfaces have a duller, more granular luster compared to silicon, and upon exposure to air it slowly begins to tarnish, losing its metallic sheen to a dark gray or black coating. This journey of slicing through the elements reveals so much, from the buttery softness of sodium to the glassy brittleness of silicon. Each cut tells a story. We saw how the alkali metals gave way with almost no fight, revealing brilliant, fleeting surfaces. We observed the denser post-transition metals which smeared, sheared, and even shattered into iridescent crystals. Finally, the metalloids showed us their dual nature, looking like metals but breaking like ceramics. By applying one simple, consistent action, we have created a rich, tactile tapestry of the elements, gaining a deeper appreciation for the incredible diversity hidden within the periodic table, one slow-motion slice at a time.